This episode of the HVAC School podcast is made possible by generous support from Testo, RectorSeal, and Carrier. Thank you to Testo, RectorSeal, and Carrier for supporting the HVAC School podcast, helping us with so many resources and really investing in technician training. And I do want to say all three of these companies make products that I really believe in. One product is the Testo 550. I've talked a lot about this set of gauges, this manifold set. It's the one we use most commonly in my business. And what you get for the money that you spend, there's just no product out there that I've seen to match it, even from just the standpoint of the fact that the clamps use a thermistor instead of a K-type thermocouple, which is significantly more accurate. And when you're wanting to measure really fine like temperature differences, like for example, the temperature difference across a liquid line dryer, where you really shouldn't have any difference whatsoever, it's really important to have very accurate test equipment. And the Testo 550 is a great product at a great price, and it's also a nice size, a size that you can actually handle. Some of the other great products that are on the market are good products, but they're very large. A lot of them use K-type thermocouples instead of thermistors. In the Testo 550, you kind of get all of it in one package. I also want to mention I've been doing a lot of conversations about AC leak freeze, the RectorSeal product, and really more and more as I test this product, we're doing a lot of testing with it. We're using it in a couple cases that make sense, older pieces of equipment that have small former carry leaks. We're testing the AC leak freeze product in that. And what I'm finding, the more I work with it, is that I really feel comfortable that it's not going to hurt a piece of equipment. Both from the Bristol testing that, Bristol did testing on the product and approved it. And so it's OEM approved by Bristol. Field Piece tested it in their S-band gauges, and they said that it's no problem. It doesn't gum anything up. So I feel really comfortable that it's the one product that I feel comfortable that we can put into a piece of equipment if it's older and it makes sense, the customer's trying to get a couple more years out of it, that it's not going to cause any harm. And above all, anything that I put into a system, I want to make sure that it doesn't cause harm. At HVAC School, we also like to partner with companies that are making innovative new products. And so we have a new product sponsor, which is the Parker Sporlan Zoom Lock product.
Meet Zoom Lock, the 10-second flame-free refrigerant fitting from Parker. Reduce labor costs by 60% with no brazing, no flame, and no fire spotter. Discover how Zoom Lock can help you be more efficient and productive. Visit zoomlock.com for more information.
And now your host, the guy who checks the air filter of every single hotel room right when he walks in, but still can't change his own filter when he's supposed to, Brian Orr.
Hey, because ain't nobody got time for a dirty air filter in a hotel room. I mean, it's one thing if it's my dirt at my house, and I can live with my own dirt, but if it's somebody else's dirt, that's just gross. Thank you for listening to the HVAC School podcast. I am Brian, and today on the podcast, we have one of our audience favorites, fan favorites, Jim Bergmann. Jim Bergmann of MeasureQuick, the MeasureQuick app that he's developing that's going to be pretty cool, and also he is the head honcho and lead product guy at Redfish Instruments. But Jim came on today to talk about airflow measurement. That's one of the things that Jim has done a lot of videos on when he was partnering with TruTech Tools, when he was one of the founders of TruTech Tools. He's done a lot of videos on that. Jim knows a lot about airflow measurement. And today on the podcast, this is part one of two. We had a long conversation, but we started with static pressure because that's one of the questions I get very often is about static pressure. And then we go into talking about ECM motors and some other things. We don't tie up all of the loose ends because that's going to be done in part two because it is a very long conversation, but I think you'll enjoy it. Here we go, Jim Bergmann. Did you like my joke the other day? You didn't respond to it. It was
your chicken joke?
Yeah, it was pretty good, wasn't it?
Man, I tell you, I don't know what to say.
You were all like,
oh
boy.
Not quite, but
no, no, that wasn't it.
I was just watching your 4th of July podcast this morning. So
my 4th of July podcast. What are you talking about?
Maybe your pre-4th of July podcast. I don't know what it was.
We just had live video.
Yeah, live
your
video.
Lingo straight, Jim.
Whatever you want to call it. Sorry.
Everything's a podcast.
Yeah, it is. Yeah, because I listen to it in podcasting, even if it's not there.
Well, thank you for taking the time to this early morning. This has got to be kind of early for you, isn't it? Don't you usually roll out of bed around 9:30, something like that?
Yeah, usually a lot later than that. So,
Okay.
Yeah.
Very good.
I like this time of year because I'm up at like 5:30 because I can't sleep if it's not completely dark in the room, and our bedroom faces almost due east. So this time of year when the sun's almost perfectly in the east, as soon as it's hitting sunrise, I'm waking up. So I don't know, my brain just starts getting active once I see light.
You're just a blue collar guy. You're just up with the roosters.
Yep. But in wintertime, man, I tell you, it's not hard for me to sleep till 8.
I don't even know what winter is. We don't have that in Florida. All right, so my thought today was talk some airflow measurement. I don't think we've really done that yet.
Okay.
So I actually got a question from a listener. Actually, it's Neil Comparetto, so I don't really know if I count him as a listener or not. He's more of a contributor, I guess. But we won't start there. I want to start with the basics. I want to start with the question that everybody thinks of when they think of, well, at least when I say everybody, most technicians think of when they think of measuring airflow. They immediately think of static pressure, which is interesting because that's not actually a measurement of airflow at all. So let's, I guess, start by just talking about what static pressure measurement is, what it's good for, and how we do it.
All right. So are we officially starting the podcast here?
I've been recording for hours. I've been recording when you're getting your coffee and fumbling with the mic and all this kind of stuff.
Oh, that's cool. All right, great. Well, let's go ahead and start. We'll start where you want to start at, even though it's not where I would start at, but it's all right.
Okay, well, let's start where I want to start, and then we'll go where you want to go. How's that sound?
Okay. So if you go back and look at our industry, I think as a whole, and why do we make airflow measurements a certain way? Static pressure is one of those you look back and you wonder why, because you're exactly right. Static pressure, obviously you require pressure in the duct to have flow, but just because you have pressure doesn't mean you have flow, right? We can obviously cap off the ducts, have huge amounts of static pressure, but not have any flow at all in the duct system. So is there a relationship between static pressure and flow? Yeah, absolutely. There's a relationship, and if we measure total static pressure across the appliance, the manufacturers measure the airflow across the appliance, then there's a relationship there. So that's all we're doing is relating a static pressure drop to a flow. The challenge with that is static pressure can fluctuate all over the place. I mean, guys have seen that you can make multiple static pressure measurements depending on where you're at in the plenum, how the duct system's designed. Sometimes you'll get negative static pressures where you should get positives, and positives where you should get negatives. So the question is, well, why do we even do it? And it goes back to this. Measuring airflow is easy, but measuring airflow accurately is very difficult. And manufacturers have decided that we don't have the tools, or we didn't have the tools back in the day to measure airflow. So they're trying to come up with indirect methods using the tools that we had that we could get airflow in the ballpark, right? So what they're trying to do is say, okay, what does a guy carry with him, a typical heating and air conditioning guy carry with him that he could get a measurement of airflow? Because obviously manufacturers know airflow measurement's critical. So they looked and said, well, the guy's usually got some kind of manometer, he's got a thermometer, and he's got a wet finger. And that's about what he's got to work with. So let's see what we can do with those tools. And that's sort of how we got to total external static pressure measurement. It's an indirect measurement of airflow, but it's got some issues. You can butt in anytime you want to butt in here, because I can ramble for hours.
Yeah, trust me, I know. I will tell you, I had one of my employees, we were talking about the checking charge without gauges episode, which, by the way, has been extremely popular, even amongst my own staff. And one of my new guys piped up in the meeting and said, man, you sure are rude to that Jim guy. I'm surprised he even comes on your podcast anymore. You're really rude to him. I thought you'd like to hear that. Apparently, any interruption of you is considered rude by the listeners, so I better just keep it zipped. I think you mentioning that airflow measurement is fairly difficult to take accurately, meaning it's easy to stick some probes in a duct. It's difficult to get an actual accurate result. And that is exactly what we're going to be talking about today, is not only taking the measurements, but getting an accurate result that you can actually do something with the data. But I want to back up real quick, because you always mentioned the appliance, and this is an important distinction, I think. So when we talk about the appliance and we're talking about a system that's moving air, that for most of us, that's either going to be the furnace, or that's going to be a fan coil or air handler or something like that. And so that's the appliance that's actually doing the moving of the air. And so the appliance manufacturer publishes some data that says, you know, under these conditions, it's going to produce this much air. And usually those conditions are going to be under a particular static pressure conditions. So this is the pressure is going to be in the ductwork or in the system. All the systems external to the appliance itself measure that, and everything else being equal, this is the output that you're going to have. But even with that, there's some things that can affect that can change, especially over time, that can cause an appliance not to produce the airflow that's published.
Well, let's back up just a second, because I think you should, when we back up, you should have a backup button that we beep as you go backwards.
That's right. You told me to do that last time, and I didn't.
I know, you're killing me here. I asked for things,
Right. All I did is just load my queue up with Charlie Sheen like that, and that doesn't work at all. I mean, that's got nothing to do with I've got this. If you get out of hand, I don't think that's helpful. So
no. So let's just think for a minute, because why are we doing this in the first place? Why are we up at 8 o'clock in the morning talking about airflow?
Yeah, up this early.
Yeah, it's a huge problem in our industry, but it is and it isn't. Because here's the problem. The problem is we're trying to do things with airflow that we've never tried to do before. Until probably, I would say, I got to be going back 10 or 15 years ago now. I had never measured airflow in a duct system. And I want to be clear about this, because when we measure total external static pressure, we're not measuring airflow. We're measuring static pressure, and we're comparing it to a rated airflow. When we're measuring airflow, we're like sticking a pitot tube in the ductwork, and we're measuring velocity pressure and then calculating an average velocity pressure and turning that into a velocity and then calculating a CFM. There's actual things we measure, like tools that you measure airflow with, like a hot wire anemometer is a tool that measures airflow. A vane anemometer is a tool that measures airflow. Or when we get into, some of the other pitot tubes, things like that, they measure airflows. But when you get into static pressure is not really a direct measurement of airflow. You're measuring a static pressure in a duct. Temperature rise is not a direct measurement of airflow. The calculation we used in iManifold, where we're calculating the mass flow across the coil, is not a direct measurement of airflow. Not saying that those measurements can't be very, very accurate, but there's measuring airflow and then there's estimation methods of airflow measurement. Two completely different things. And there's variables that if we don't take into account, that we're not going to get an accurate measure of airflow. Well, why does that matter? Because at the end of the day, going back with equipment, let's say 20 years ago, when we weren't measuring airflow, we were just going in and we had 4 speeds on a PSC motor that we had to pick from, right? So we just needed to get, if you really think about it in a nutshell, all we needed was an airflow measurement accurate enough to pick the right tap on the blower. That's all we needed. That's all we cared about. So, we had high, medium high, low, and medium low, and which one did we need to pick? So we took a static pressure reading, we threw it in a ductwork, we go, oh, this one's about 800 CFM, and I got a 2-ton system, so I'm going to leave it on my medium low tap, and there, I'm good to go. Or my medium high tap, and I'm good to go. It was pretty much that simple, because what have we changed, Brian, that we have never done? I think probably the biggest change iManifold, when we designed that tool, brought to the industry. This is something we'd been doing. In fact, if you talk to Bill Spohn, this goes clear back to when I first met Bill and met Testo, because honest to goodness, when I started reading chapters 1, 2, and 3 in refrigeration air conditioning technology and ran across, the specific heat formula, the sensible heat formula, and the total heat formula, and I tried to apply those in the lab. And what we were doing was temperature rise test. We're trying to calculate CFM through temperature rise. And then all of a sudden it's like, hey, one of my students, Matt Scheffler, is like, hey, Bergmann, if you can use this formula to measure airflow, could we rearrange it algebraically and measure capacity with it? And I'm like, yeah, sure, Matt. So let's go out there and do that. So we went outside and we make all these measurements. We're using things like total external static pressure and temperature rise to get airflow. And we're doing all this, and the capacity is like all over the place. And not only is it all over the place, but we can't even get the same answer 2 times in a row. So I'm sitting there telling Matt, I said, well, some things are only meant to be done in a lab, I guess. And he goes, well, we are in a lab. And I'm like, yeah, I guess we are in a lab, but maybe a different kind of lab, Matt, like a scientific lab. And I'm sitting there thinking after the kids left school, I'm like, dang, man, I'm in a huge building. Not only my lab, but all my ceilings are connected throughout this whole building. I'm not changing conditions in this building. So I can run these furnaces or air conditioners all day long. My units are in the shop, so I'm absorbing and rejecting heat in the same place. I'm like, how come I can't get an accurate airflow measurement? How come I can't get its capacities right? What the heck is going on here? And really came down to, this is where I had an epiphany in my life and figured out, my goodness, it's all coming down to I'm not getting good measurements. And, I got Testo in my lab, and also we got accurate temperature and humidity measurements. All the science and all the math started to work. And then I started realizing the challenges with each one of these different types of airflow measurement methods. Because we can also measure static pressure drop across the coil, static pressure drop across the filter, total external static pressure drop across something. Anything can be rated for a static pressure drop and CFM. The manufacturer can do that. The problem becomes with using that as your primary measurement of airflow is it's accurate enough so you can get the right blower tap, but it's not accurate enough to do things like capacity testing.
Right.
This is where the challenge becomes. is people are trying to use measurement to do things they've never done before, and they can't get the measurement to make any sense. Like they're going, how am I getting 2.5 tons of cooling out of my 2-ton air conditioner? Wow, this is just impossible. Then they make the measurements again. Now they're getting, 1.8 tons out of it. It's like, what the heck's going on here? They measure it again. They're getting a different measurement, and they're getting frustrated with it. And they say, oh, that can't be done. You cannot measure capacity accurately in the field. It's like, well, really? Really? Because I think AHRI measures capacity. I mean, they're a third party. Yeah, they got some pretty cool stuff. But today, when you look at instrumentation today, like what we get from just digital instruments in general, not all digital instruments, I don't want to go out there, but sensors in general have dramatically improved. I've used some of the stuff Testo makes, some of the stuff Fieldpiece makes, stuff that we did with iManifold, stuff that we're seeing CPS come out with. They're all reasonably accurate. Now, obviously, the more money you spend, the better sensor quality you tend to get. I've seen on the smart probes, like their 605i, that thing is absolutely incredible for relative humidity and temperature. It's probably one of the better sensors I've seen out there. But in general, when you're talking about sensor quality, the more you pay for an instrument, the better the sensor is. The electronics are really the cheap part of an instrument. It's actually what we're paying for is the sensor. And when you get into things like measuring airflow, with a pitot tube, I don't know if you've ever tried a pitot tube before, but it's a real pain because the measurements are so tiny, and that's because the sensors we have aren't accurate enough to measure those really low pressures. Right. Typically, you use like an incline manometer or something like that to measure that. When we're looking at a total external static pressure, and we're dealing with, like say 1/2 inch to 1 inch of static pressure, when we're working with a pitot tube, it's like 0.02, 0.01 inches of water column velocity pressure, right? So it's a totally different type of measurement. It requires a totally different type of tool. Then we're getting to like a blower door gauge. So where you might spend $175 or $100 for a little pocket digital manometer, you're going to spend $1,000 for a blower door gauge, right? And what is it? It's the accuracy and resolution of the gauge that you're paying for. That's why high quality instruments cost more money, but we can do other things with them, like calculate capacity accurately, where we could never do that with the tools we had with like standard YouTube manometer to measure static pressure and wet bulb sock. Guys are still out there with K-type thermocouples and wet bulb socks trying to measure wet bulb. And not only they're using the wrong tool, but they're doing it with the wrong process. They're using water that's out of the tap instead of distilled water. Their cotton sock is not clean. They are sticking in an airstream where the air velocities, instead of being 500 to 600 feet per minute, it's 1,200 to 1,500 feet per minute. So the water's evaporating faster. It's affecting the wet bulb temperature. All those kind of things come into play. So the instruments are critical, but also what are we trying to do with the measurement? And I think that's when we start with this, and just sort of I'm dragging you along because static pressure is a good place to start because it got us primered there. But the key thing is, what are you trying to do with the airflow measurement? If we're an installer, I'm sure you have install crews, and you're going out there and you're just getting this thing set up. Hey, total external static pressure is perfectly fine. The guy can go out there and all he's got to do is get it set on the right blower speed and he's good to go. But if you're sending a service tech out behind him because the customer's complaining, the equipment seems to be running too long, right? The house is cooling, but it just seems like it runs forever. I just want somebody to come out and check it and see if it's working right. Well, if that guy's going to go out and do capacity measurements on the equipment and make sure that everything's working properly, a measurement of static pressure is definitely not a suitable measurement because that could throw your capacity readings off by 10, 20% easily. Because if your airflow measurement's not accurate, nothing else is going to be. Because it's straight multiplication, right? If just on the standard air formulas, 4.5 times CFM times change in enthalpy. So that CFM, when we multiply it through, any error multiplies straight through also, and you get a lot of uncertainty then in your equations. So that's what we're trying to eliminate here when we're talking about different airflow measurement methods.
Right. And so you pointed out there are a couple different reasons why we look at airflow and a couple different use cases. So in a lot of cases, an installer just wants to make sure that the equipment is producing the correct CFM. So they're just setting a charge based on the charging information that the manufacturer provides, and they're wanting to make sure that the correct CFM is being produced. So the correct fan tap in the old way of thinking of it. And so that's sort of the simplistic way of looking at it, because the installer's not necessarily or generally not going to do delivered capacity tests. They just get everything within range, and there's the assumption that the equipment's working properly. And again, that's just standard practice. Maybe some people will say, well, our installers do, that type of testing every time. But let's talk a little bit about, because I think there may even be some misunderstanding about static pressure, how it works, what we do. So let's just break it down to the very simple steps. So when you're measuring static pressure, you're taking a manometer, generally a dual manometer, and you're putting the negative probe in the return side, you're putting the positive probe in the supply side, and you're measuring that total external static. First off, because this is the question I get most often, where do you put the probes in order to measure what the manufacturer of that appliance is going to consider appropriate total external static?
That's a simple question, but also like the $1 million question, because let's just make sure that we're talking the same thing here, because all this depends, right? Like I'm up here in the Northeast, up in Ohio. We have primarily furnaces that we're going to measure total external static pressure on. So when you typically look at how an appliance is rated, it's rated as the appliance itself. In other words, a furnace in the north doesn't come with a coil. That's an accessory item, right? We can heat homes or we can cool homes, but typically the furnace and the coil are two separate components. So the furnace is rated by itself. The coil is rated by itself. But if you go down where you're at in Florida, where you heat primarily with heat pumps or electric strip heat, and you have an air handler, it's typically rated with a coil in it, right? So we got two different configurations. You got a rooftop unit. It's rated with a coil in it, right? We're going to be measuring supply and return air static. But on a furnace, a gas furnace, we would not be measuring in the supply and return air plenums like we would on an air handler or on a rooftop. So it really depends. You have to look at your manufacturer's guide, first of all, and see where do they want you to measure the total external static pressure. That's pretty important. Now, in the case of a furnace, which we'd have here, we'd have to be below the evaporator coil and we'd have to be in the return air. And we've petitioned manufacturers for years to actually put multiple static pressure ports in a piece of equipment, because obviously, it depends on how the equipment's hooked up. You can have a return duct in the side of a furnace. You can have it in the bottom of the furnace, left side, right side, so you need multiple points in there. Also, you would have multiple duct configurations, which also affect the airflow. And just to put this in perspective, because a lot of people don't quite understand how that happens, I just want to give you guys a visual of what happens. When you have air going through a duct, right? And I think probably the easiest way to imagine this is imagine a racetrack, right? If we go out and we watch NASCAR where they're driving in circles all the time, and we take that track and we just say, you know what? Instead of having circular corners, I'm going to make square corners out of this race car track. 200 miles an hour, people are flying around the racetrack into square corners, right? Well, if you're on the inside of the track and you try and cut that corner, you're going to start to spin out. And you're going to have turbulence as you go around that corner. Cars are spinning out. Some of the cars are going to make it through the sort of the center of the turn there. If you're up the upper part of the track too, when you hit that corner, 200 miles an hour, you're going to either smash it, you're going to probably smash into that wall, you're going to slide in the wall. So you're going to have turbulence up in the two corners where you're at, in the two square corners. Because you got to figure the track's like a giant rectangle inside of another rectangle, right? I mean, we've got width to this duct here, this track. And as cars are zipping around there, if you're in the center of the track, you have a good chance of getting through. But if you're on the outside or the inside of the track, flying around that corner there, you're going to have some problems. It would definitely make NASCAR more interesting, but it would also be a lot more expensive, right? Because cars would be totally trashed out here. And that's what happens when air is going through a duct. When we don't have good air design, there's a lot of turbulence going around the corners, and the cars are spinning out, the air is spinning out. Well, that air, as it spins in a duct, can actually create negative pressures in the ductwork, because it's just like you're standing at a bus stop, you're watching a bus come by, and you don't ever feel the bus coming, but as soon as it passes by, you get the suction of air. You feel, this pull of air from the bus. That's the Bernoulli effect. It's just entraining air behind it. So air at high velocities, when it's zipping by stuff, creates a negative pressure behind it, and we can feel that air spinning in there. Well, that affects our static pressure measurement. So earlier, I said you can get different static pressure measurements by putting your probes in different places in the duct. Well, that's 100% true, because as the air is turning, what you're going to find out is it's creating different pressures in that duct system. So we don't get this like smooth laminar pressure like we envision in our head, where there's just this constant suction, because the air is also under velocity. It's moving, crashing, spinning through that ductwork, and those velocity pressures are going to influence our static pressures. If we just had static pressure is bursting pressure, right? If we were to take a balloon and we were to blow it up, and put a static pressure probe in there, that is truly static pressure. It's the pressure that balloon is just sitting there in its static position. There's no flow in that balloon. It's just sitting there, and it's a static pressure reading. Now, static means standing pressure, just not moving. There's no change. Velocity pressure is now we let go of that balloon, and that static pressure all of a sudden converts to velocity pressure, and the balloon zips off and flies away. That's the velocity pressure. And as the air exits that balloon and it creates turbulence in there, we no longer have this nice, stable, static pressure. We have this static and velocity combined, and that's what influences and screws up our reading. So at the end of the day, when you ask, well, where do I put my static pressure point? Well, let's say you're on the return side of a furnace. The center of the fan, like you have obviously the inlet of the fan, and you have the housings called the volute, where the air goes into the fan housing, and then you have the exit of the fan. You don't want to be near the inlet of the fan. So if you drill a hole in the center of the duct, think about what's happening. You got a blower there. It's turning and spinning. It's creating like this little tornado inside of the duct. If you can visualize that blower spinning and air turning into that fan, spinning around, it's creating a vortex. It's creating a little tornado inside of that duct as it pulls that air in. And that center of that tornado is at a higher negative pressure than it would be elsewhere in a duct. Ideally, you want to be somewhere in a corner away from wiring. That's the other thing we don't want to do. When I'm drilling a hole inside of a furnace, no matter where I'm drilling at, I usually take a piece of electrical tape and wrap it around my drill bit so I only go through about 1/4 of an inch, because I just need to pierce the steel, right? I don't want to drill into the wiring. If you want to put a washer on, even as a stop, you can, so you don't get the electrical tape goo on your furnace. But that way, when you punch through the steel, you just get through there. But, drill in a corner or something like that. Now, the second thing you got to realize is a lot of those cabinets are insulated. So also we got to get past the insulation. So you got to take a screwdriver or something and poke through that insulation, make sure that you have a good hole. And then obviously you want to use a static pressure tip. And a static pressure tip is different from a pitot tube. A static pressure tip just has holes around the outside of the tip. And there's a lot of holes in there, so it tries to average the pressure. Again, it's really dependent upon where you put it. And if you have a piece of shop equipment you can try this in, just drill a hole, like right in front where the blower would go, and then drill a hole in the corners and look at the pressure differences in the return. And you'll see that it can have a lot of influence on where you put it. So where do you want to put it? In a place in the duct system where there's not a lot of turbulent airflow. So you want to be away from the corners where the air's coming in, but around, like if you go in an opposite corner, like say your inlet is on the left side and your duct inlet's on the left, then measure on the right side in a corner down there somewhere, because there's no flow of air through that. And the blower's creating a suction pressure on there, and that's what we really want to measure. Uninterrupted flow, laminar flow, or being in a laminar flow section of the duct. So it's not influencing our static pressure readings. Same thing on the supply side. We want to be in a place in the furnace. So like in the back of the furnace is less than ideal, because where the blower is blowing up the back of a furnace, if you look in a cabinet, the outlet of the blower is usually all the way towards the back, so you get higher airflow over the back of a furnace than you do over the front of the furnace, right? And again, we're trying to measure pressure in there, so maybe go to the left or the right side of the furnace, but not directly in the back in the middle, below the evaporator coil, because you're going to be right in the airstream coming off the blower, and that's going to be probably more turbulent air than you would get on the side of the furnace. Because again, we want to measure the pressure in the supply, we want to measure the pressure in return. The manufacturer has done the same, and they've measured pressures at corresponding flows. So all you're doing when you look at a static pressure chart, you're just comparing the static pressure measured to the flow measured, usually using the tap, the speed tap that you're on, and it'll tell you what your approximate airflow is. But again, that's accurate enough to select the right speed for cooling, let's say, but it's not accurate enough to measure the performance of the cooling. You'll get a lot of error in that if you use that for your primary airflow measurement method. Again, I always like talking measurement or estimation. So static pressure is an estimation of airflow, but it's got its place, and that's for your installer to get the correct blower speed.
A couple things. So just to sort of summarize this, first off, in a furnace, you're reading below the furnace. So that would be after any additional filter racks that are installed on the return side. If you have a 3-inch or 4-inch filter that you've added in, then you need to take your measurement after that 3 or 4-inch filter.
Yeah, usually the furnace is rated with a filter in place, which, you bring up another good point here, is that when you're looking at like static pressure readings, they're under very specific conditions. So it's with a certain type of filter. Typically, they're rated with like a fiberglass throwaway filter or a hog hair filter, or a filter that's got very low resistance to flow. If you put in, like a space guard filter or a 3M filter that's got a higher pressure drop, it's definitely going to affect your static pressure readings across your furnace if you don't take it in the right location, right? So if the furnace is rated with the filter or without the filter, and the manufacturer will tell you with or without, again, it's going to mess with your readings. So if they're rated with a standard filter, then you might have to include like 1/10 of an inch of static pressure drop for the filter to normalize the measurement for the static pressure drop.
Yeah, and it's not always super apparent. Like when you look in Carrier's fan coil specs, like it talks about the factory installed filter pressure drop on their filter, but it doesn't readily say, is it rated with it or is it rated without it? Now the amount is, nominal. So you're looking at anywhere from, I'm looking at this chart right now, anywhere from like 0.02 up to almost 1, depending on the CFM on that particular filter. So there is some variance there, but it's not always super readily apparent. But the important thing to know is if you're adding in a filter.
You meant 0.1, right? 0.02 to 0.1, not 1.
What did I say?
You said 1.
I said 1. 1 would be very high. That'd be a very restricted filter, Jim.
Yes, very.
So if you're adding in an aftermarket filtration product, that's where it becomes even more important because you could have significant pressure drop across some super cherry bomb, Betamax, double pleated MERV 14 filters. That you might
nothing gets through this filter, including air. So
right. Which comes down to what I actually did used to say to customers, which probably wasn't the best thing. Customers would always ask, well, what's the best filter to put in? What's going to catch the most? And I would say a brick wall. And then just wait. And they would blink. And then I would say, but no air will get through either. So you got to kind of find something in between a fiberglass and a brick wall.
Mm-hmm. Yeah.
They would just be crickets. And then I would lose all my customers. I wonder why.
This is why you're in the office doing podcasts, Brian.
This is why I'm in the office doing podcasts, right? Exactly. Because I couldn't sell any filters. The way I've heard you say it before, and I like this way, is you're measuring on both sides of what's in the box. So a furnace comes in its own box. And so the furnace is rated, so you're measuring directly above the furnace or in the furnace cabinet itself, and then within the furnace itself. So you're measuring what's in the box. In the case of a fan coil, air handler, RTU, whatever, what's in the box already includes the evaporator coil, already includes a factory filter. And so
with a caveat there of what it doesn't include is your electric strip heat, which is in a different box. And as soon as your installer puts electric strip heat in an air handler, he's just changed the rating of the air handler, the design of the air handler. So now he has to go to a different chart that says air handler with this electric strip heat, and then it's going to give him a whole new set of static pressure readings for that configuration of the air handler, right? So there's a lot of charts in there, and they get relatively confusing because you got to look at model numbers. You've got to look at heater model numbers. You've got to look at maybe evaporator coils that are installed. You've got to look at filters that are installed. So like I said, sticking probes in a duct is very easy, but getting an accurate airflow measurement is not. This is why also, when you go out there and you buy, let's say you were to take a single speed air handler and do total external static pressure, measure the airflow, and then take a hot wire anemometer, measure the airflow, and then take a pitot tube and measure the airflow, and then take a vane anemometer, measure the airflow, and then buy a true flow grid, measure the airflow, and then do static pressure matching method with a duct pressure tester to measure airflow, and then do temperature rise with the electric heat to measure airflow, and then put the eye manifold in and 2 probes and supply and return and measure airflow, you would get a whole bunch of different readings. Now, they would all agree within some semblance of something, but they would all be a little bit different. And the reasons are each measurement method has its own measurement uncertainty. Each measurement method has its own corrections that need to be applied to it. Some of them are dependent upon the air density, and some of them measure independent of the air density, which is the other thing I want to harp on before we get too far into this. The challenge becomes, guys say, I can't get an accurate airflow measurement because I measure it using these different methods and I get all these different results. Well, the challenge becomes is you really have to understand each method intimately and what affects it and how to correct it. What's interesting is tab guys that are actually, test and balance guys that are formally trained in air and airflow measurement. They actually go to school for 3 to 5 years, typically in like a union apprenticeship, to learn how to measure airflow accurately. And they have a manual that's probably 1.5 inches thick that goes over all the different methods, even like we didn't talk about RPM and static pressure on a commercial rooftop unit, where we can measure the speed of the blower. with a tachometer. There's all these different methods. These guys are trained in those, and then they're trained to normalize those measurements or correct those measurements for the variables that impact them so that they can compare one measurement method to another and then make corrections that normalize them together. Best example I can think of this is you're really close to the ocean sea level, right, Brian? So
Yes.
If you were to go on the Weather Channel right now and look at the barometric pressure, it would be 14.7, let's say, because you're at sea level, right? Your barometric pressure is 14.7. Well, if we go and look at the barometric pressure on Pikes Peak, which is 7,000 feet above sea level or so, you would find out that the barometric pressure is also like 14.7, 14.2, something. You're like, well, how is that possible, right? How is it possible to have the same barometric pressure at sea level as we do on Pikes Peak? Well, because they normalized it to sea level on the Weather Channel, right? They just said, well, we're just going to normalize it for everybody's barometric pressure for elevation, so it's all relative. And this is the kind of thing we do in the air conditioning industry is we've normalized things and people don't realize they've been normalized or they haven't been normalized or they're the wrong equation. Like we talk about standard air equations, the ones guys are using to calculate capacity, 4.5 times CFM times change in enthalpy. Well, that's a standard air equation. That's standard air, which means 68 degrees Fahrenheit, 0% relative humidity at sea level. Well, when are we ever at sea level and at 0% relative humidity? Not very often, right? So that standard air formula has some error in it that if we don't correct for it, we're going to get some inconsistent results. Our industry's rampant with those kind of things. And the challenge becomes, again, it goes all back to this. You have guys that had extremely expensive laboratory equipment that were setting up stuff in the lab, designing, engineering this stuff. I mean, you look at the work Willis Carrier did, and I'm completely amazed that the psychometric chart he developed, around 1915 or so, hasn't substantially changed. I mean, they've gotten a little bit tighter. ASHRAE's done a heck of a job getting a little bit better than it was and taking it really to the next level. But substantially, he figured out almost everything on there. Well, how did he do that? He did it by continually eliminating variables that were influencing his temperature measurements and his humidity measurements. And when we look at the tools that were available to us, from 1915 or available to the technician from 1915 all the way up to probably, 12, 14 years ago, we just didn't have field grade instrumentation that could give us laboratory results. And that, I guess, again, has completely changed. What's available to us today is much, much better. Now, again, you have to make a little bit of investment into airflow measurement tools and things, but you're going to get much, much better results at the end of the day. But you have to learn how to use those tools and the limitations of each one. And the manufacturer's probably not going to tell you what those limitations are because they may not know, or they may not think you care, or they may think, like in the case of Testo, that everybody that handles an instrument is formally trained. It's very interesting when I worked for Testo and went over to Germany. I found out you can't be a technician unless you've gone through like 5 or 6 years of training. Same thing in Canada, I believe. You have to have formalized training. Where in Ohio or Florida or things like that, I mean, you may have to get a contractor's license, but that doesn't mean you've been formally trained in anything except for business and maybe how to do a heat loss calculation. It doesn't mean you have a thorough understanding or you've been to a trade school or you've been to college or you've had some kind of formal training on how to do these things. And this is where we fall down in our industry because we're, again, people buy a product, they think just because they get an output of X CFM or X degrees or X humidity that, well, it's got to be correct. I'm telling you right now, not necessarily, because you have to understand the tool you're using.
The tool you're using and all of the environmental variables that exist that you're not.
And I'm sorry to make this hard, but it goes back to what I said at the beginning. Making measurements is easy. Making them correctly is pretty darn hard. I guess if anything we're going to generate in this podcast, it's awareness that you're not alone in your frustration, that I know you've been trying to measure airflow and you just don't seem like you can get it. It's because you need to study it more and you need to spend some time learning about the variables and you need to spend some time, like I set up equipment in my house or garage or big area where it's not going to influence temperature. And I could continually play with it all day long and figure out what the heck's going on here so I can get consistent measurements and try and make those corrections. And it's going to take you time. There's no doubt about it. But once you start to understand it, and I honestly think this, if you understand airflow, you will be one of the best and most sought after technicians in the industry because 7 out of 10 systems today do not have correct airflow. period. 7 out of 10. They've done multiple studies. California, Energy Star. I got probably 6 different studies I could cite. They consistently show the same thing. 7 out of 10 systems have incorrect airflow, primarily due to poor duct design. That's a big thing in California, Florida, Texas, a lot of the coastal states. Because of the way homes are constructed and materials used, it seems to be a big problem out there. But those airflow issues are the ones that typically go unresolved because technicians get what I like to call as appliance fixation. And what that means is they stand there at the appliance and they look at the furnace, or they look at the air handler, they look at the condenser, and they forget that is only part of a system. And they need to look at the things that are attached to it, like the ducts and the line set and the electrical. There's electrical distribution systems, there's air distribution systems, there's refrigerant distribution systems. You got to look at everything because it's all part of a system. When we're just looking at the air handler and trying to fix all the airflow problems at the air handler, it's like trying to change somebody's heart out and put it on a bad set of arteries, clogged up with plaque and gunk in there. It's not going to fix the problem. Adjusting the blower speed is probably not going to fix the problem if you're running 1.5 inches of static pressure already, or 1 inch of static pressure already. You have duct issues that need to get resolved. And these are, on a sidebar, these are some of the challenges that we get. But these are the things, if you're doing your airflow measurements and you're looking at your appliance, you got to start thinking of the entire thing as a system and not just as an appliance. Even though some of the measurements we're going to make are at the appliance, you have to look at everything that's attached to it and think about what's happening as you're making your measurements.
All right, so something I want to mention that's changed over the last mostly over the last 5 years, but really over the last 10 to 12 years, as we've started to see ECM Motor Technology come into the marketplace. Again, this is my opinion, and I'd like to hear if you have a different one, but it has become a little easier to get accurate airflow output, accurate CFM output based on static pressure, only because there's less variability in the output. When you're dealing with an old PSC motor, an old typical, multi-tap inductive motor that we typically work on, there's large variance depending on the external static pressure on the system. Whereas if you look at a fan curve nowadays on, say, a variable speed, say a Carrier FV or FE air handler, the airflow output is very, very consistent until you hit about 0.9 total external static. So that's that's pretty high static. Now, that's not good because the wattage is higher on the piece of equipment. You're producing more heat out of the blower motor. So it's not good to have high static, but it at least makes it easier to measure and estimate the airflow. Would you agree with that statement, or would you add anything to that?
No, I have a lot to add to that.
Go ahead.
Yeah,
please do.
So the ECM motor is probably the best invention this industry's had in the last 50 years, maybe the last 100 years, as far as air movement technology goes. But I think we need to go back and understand a couple of different things, because PSC motors and ECM motors are way, 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 way different. But first of all, it's time for you to get uncomfortable in your seat, because I'm going to start quizzing you again. Yep.
Or the audience?
No, you.
Or am I just a proxy for the audience?
You are a proxy for the audience. Yeah, I think that sounds good.
Okay.
Although you may not be reflective of the audience, but we'll give you a shot.
I'm an everyman, Jim. I'm an everyman. I'm a blue-collar guy.
All right.
Just a regular blue-collar guy sitting here. I'm wearing my steel-toed work boots right now.
All right, so let's ask a couple of questions. Let's first of all think through this logically. It might be hard for you, but we'll give it a shot.
Okay. I'll do my best.
What is the work that the fan does?
The work that the fan does is it moves air.
Okay, perfect. It moves air. And let's go back and just ask one more question. What kind of air does it move? Does it move CFM of air, or does it move pounds of air? Or does it move both?
It moves both.
It does, but does the CFM on a PSC fan, let me think of this way. Does the CFM of a fan remain constant with the air density of a PSC fan? Have you ever thought about that before? Don't you know? Never even crossed your mind.
It remains constant with the density. I'm trying to think of how to say what I'm wanting to say here. So it moves air independent of density.
Right. So if we're talking about boxes of air, if we have a fan that moves 1,000 boxes, 1,000 CFM, right? It's got to move in 1,000 of these cubic foot boxes. The fan doesn't care what's in the box. It's just going to move the same 1,000 boxes. And as the air density changes, it's going to have a constant CFM at a variable mass flow rate, right? All right.
Right.
This is my biggest frustration in the HVAC industry as far as airflow goes. is what we're not teaching technicians. You know, it's interesting if you go to chapter 1 of the textbook, Refrigeration, Air Conditioning Technology, they take you through and they say, well, Q, equals quantity of heat equals your mass times your specific heat times your change in temperature. And we're talking about mass flow formulas. And then all of a sudden, we switch over and tell technicians, an air requires 400 CFM per ton. What they aren't doing right there is saying, okay, this is, first of all, standard air. So when we look at that 400 CFM per ton, it's standard air. So that means 400 times 0.075 pounds per cubic foot, because a standard cubic foot of air is 0.075 pounds per cubic foot. That's the weight of the air. So 400 times 0.075 is 30 pounds per minute per ton, right? 30 pounds per minute per ton. So if you've got 400 times 0.075 is 30. Right? So that's what you're looking at. So you're talking about 400 CFM, cubic feet per minute. You're talking about 30 pounds per minute per ton. Okay. So if we're talking about a 5-ton system, we're talking about 150 pounds of air per minute going across that coil. It's the mass of air that we're moving. So we're talking about what that blower's doing. It is moving CFM of air, but it's actually moving these pounds of air. That's why it takes horsepower. It takes work to move that air. We're moving pounds of air through the duct. And people don't often consider that because we don't feel the weight of the air around us because it's exerting the same force in all directions. We can feel a little bit. If you take a piece of cardboard or something, you wave it through the air, you can feel the resistance of the air. That's the weight of the air pushing back on that cardboard. But overall, we don't think about air resistance or air movement all that much. And that's what we're doing. We're pushing air through a duct system is we're moving pounds of air through the duct system. That's the physical work that we're doing. So going back to our PSC motor, we're just talking about static pressure. Obviously, if I'm moving air through a duct, I'm going to have some work that I'm doing. And that work, we normally represent that in watts of power. So we have a constant voltage and we see our amperage go up and down as we increase or decrease the airflow, right? So if I clamp my amp meter on my blower, I'm going to expect to see an amp draw on there, right? So let me ask you a question. If I block my supply duct off completely, just cap it off, what's my amp draw going to do?
Your amp draw is going to go down, Jim.
Oh, okay, very good. And if I block off my return, what's my amp draw going to do?
It's going to go down.
Right. Why is it going to go down? If it sounds like the motor's working really hard. I mean, I can hear the pressure. Mm-hmm. The pressure's going way up.
Sucking like crazy.
Sucking like crazy. Yeah. It's got to be doing a whole bunch more work. Now, why is it that it's not?
Because you're moving less pounds of air. You're giving it less pounds of air to move.
Right.
That's the work you're doing.
That's the work. Yeah. Everything goes back to mass flow. It's great you understand this because a lot of people have never measured this or we make assumptions. I made assumptions for years. It was always fun when I was teaching class because I'd go out there. I don't care whether you're a service technician or you're a teacher or whatever you're doing. When you're in a position of authority, you have to act like you're an authority. So those of us in this industry that have been around, that's one of the things you learn, like when you're going out to talk to a homeowner. When you tell them something, you're telling them something with authority. And when you tell another technician something, you're telling them with authority. And so when I go out there and I tell my students with authority, well, this is what's going to happen. Then we go out and we put a damper in a supply duct and I put my amp probe on there. It did opposite of what I thought it was going to do. I felt like an idiot. But these are things that we all sort of go through in this industry is we make assumptions about how things work without actually making measurements. And once we figure this stuff out, it really changes our career because this is important stuff to know.
Well, one thing, so let me add this, because the first time that I noticed this, and I'm sure every technician has noticed this with a typical PSC motor, is that when you try to check the amp draw with the blower door off, you'll notice that your amp draw is high. In some cases, your motor's even overamping. Then you put that blower door on, and if you can measure it with the, you take the panel, put it sideways over the blower compartment, and then measure. And this is mostly because I've worked on fan coils most of my career, air handlers most of my career. And you'll notice that the amp draw goes way down. And that's because with the cover off, you're giving it a lot more pounds of air for that blower to move, which then increases your amp draw.
You've removed the restriction of the ductwork, right? I mean, that's what you're saying. So in a sense, what you're saying also is that you probably had highly restrictive returns. If you would have had returns that were sized larger, or, sometimes I will admit, you take the air handler cover off and it's such a huge opening with that door off because you're just trying to get the fan out and things like that, yeah, you can definitely see an overamping. You'll see that a lot on like rooftop systems and things like that.
Like you mentioned, though, the reason that is because I'm dealing with products that were designed with a coil built in.
Right.
And so I'm actually removing the coil from the equation too. So I'm actually, when I take the panel off, I'm giving it less static pressure than it was ever designed to have.
Right.
And so it's going to move more airflow than it was ever designed to move.
Right. Yep. And that's why you're going to see that amp draw to fluctuate. But so far, you're acing the quiz here.
I'm doing better than last time?
Yep. Yeah. Well.
Okay, good.
So the next thing is, let's talk about an ECM motor, because an ECM is different from a PSC motor in that an ECM motor, there's multiple flavors of them. But let's just talk about the ones that are the programmable, the programmed ECM.
Fully variable.
Yeah, fully variable speed, right? So an ECM is different from a PSC motor in the fact that an ECM will speed up to try and move a constant mass flow across the coil. Now, here's the thing to understand with an ECM motor or an ECM fan, not so much the motor, but the whole assembly, the motor and the fan together. ECMs work off RPM and torque. So the manufacturer of the ECM motor or the blower has said, okay, at this RPM and at this torque, which means amp draw on the motor, we're going to move this amount of CFM. It's all programmed in, it's mathematical equations, and that's why every single motor has to be matched to a fan. That's why these things aren't interchangeable. It's all designed as a system to go in a very specific air handle or a very specific furnace. So important thing about ECMs, you have to have the right motor for the right air handle or furnace. They're not a universal drop-in because it's an engineered system. So the ECM motor, when it sees that its amp draw is dropping, immediately the ECM knows that, I'm not moving as much air as I should be moving. And the ECM does something different than a PSC motor. The ECM starts to speed up to increase its torque. Now, obviously, the PSC does also, but not in the proportion that an ECM does. PSC is going to start to speed up because you're unloading it, right? Because it's not going to have as much motor slip and things like that because we're not doing as much work. But when we're talking about an ECM now, it's speeding up the fan to try and move more air, to try and keep the mass flow or the airflow rate across the coil the same all the time. And so where a PSC motor is going to start to drop off its airflow, ECM is going to try and speed up and keep the airflow the same all the time. Now, the other cool thing is with the ECM motor is as our air density changes, the ECM, especially if the air density drops, the torque will go down, the ECM will speed up to try and keep the mass flow rate across the coil the same all the time. So the ECMs can always move 30 pounds per minute per ton. So when we're talking about standard air, right? Because if you used iManifold, you're going to see it's got SCFM and ACFM, two different readings. Standard CFM per ton means 400 times 0.075 or 30 pounds per minute per ton. That's the standard air that's going across the coil. It's designed to have 30 pounds per minute per ton. Now, the actual amount of air required to do that may be much higher because if the air density drops, it's going to require more CFM to keep the mass flow rate the same across the coil. So sometimes you go on a programmable ECM, like the Carrier ones, or like I have one with a communicating thermostat. My system's a 3-ton, so it's rated at 1200 CFM. Sometimes I'll see it's running 1250, 1275 CFM. Run a little higher than normal. And that's because the air density's dropped and the ECM's dropped in torque. So it's moving more CFM to keep the airflow rate the same or the mass flow rate the same across the coil. Everything in our industry comes down to mass flow. And like I said, we've been trying to measure airflow, and airflow and mass flow are the same, but different. You can have a constant airflow with a variable mass flow rate. And that's what people need to understand is that when it all comes down to the end of the day, we're not cooling the CFMs of air, we're cooling the mass of air across the coil. And that's the critical thing. If you convert everything back to mass flow, and that's how you'll see like evaporator coils are actually rated. They're not rated with CFM, they're rated with mass of air across the coil. The industry would be a lot easier to understand, but it's just sadly not the way that we taught everybody in the HVAC industry. So the ECM, in a closing, I guess, or in closing at least this particular thought, the ECM is much better because it's going to keep the mass flow across the coil constant, which means that if we have better airflow, we're going to have better cooling, we're going to have better control of the system. But we do that at the sacrifice of the duct system is restrictive. The ECM is going to obviously draw more amps to get that air moved across the evaporator coil that it needs, right? Now, some ECMs you're going to find out they aren't necessarily speed limited. So sometimes you'll see blowers actually completely come apart, right? I've seen pictures online of blowers that have completely blown apart. Well, why does that happen? Well, that blower is spinning so fast trying to get that airflow up that it actually, the centrifugal force has torn the blower apart. So when you see blowers disintegrate, blowers come apart, that's typically because you have a system with very high static pressure and the ECM is trying to go as hard as it can to try and get that airflow up where it is, and it just simply cannot overcome it, and things start to break. That's why we see ECM failures. They're usually running on systems that have too high a static pressure. Again, this is a furnace fixation. The guys go out there and they see, oh, the ECM's bad. Boy, I've changed out 13 ECM motors in the last month. These things are garbage. It's like, did you ever think maybe it's the duct systems that they're attached to? Because, ECMs have been around for a long time. I know a lot of people that have had them for 20 years plus in their furnace, that these things aren't falling apart. They aren't breaking. Fan motors in general, they'll run forever as long as they're kept clean and they have adequate airflow across them and they have good duct systems. Motors run and run and run and run. It's the times that we don't design the duct system properly and we cause all these other issues, that's affecting our failure rate. So,
yeah, I'll say a couple different things about that are just kind of field specific. The one is that ECMs have been out for a long time, and we didn't see a really high fail rate on ECM until the X13 came out. And I think it was probably due to two things. I think there were some legitimate issues, especially relating to moisture getting into the way that the wiring plugs and harnesses were set up, and some moisture getting into the actual X13 motors, which they've since changed, and we've seen the failure rates go way, way down. But then also, when a technology becomes essentially ubiquitous, when everybody has it, well, then there's just much more chance that you're going to see a lot more of them fail. And so as X13 motors, which are not the programmed variable speed, but they're still a constant torque motor, as those have just gone all over the place, we've seen a lot more of them fail, which I think is a combination of a couple different things. But you're right in that if you have these things running higher RPM than they need to, that's going to increase the odds that things go wrong. It just is. They're going to get hotter. Things are going to be spinning at higher RPMs, which means that it's more likely that stuff flies apart. So you still want to make sure that you're designing duct systems properly. But the nice thing, and what I was getting at here with the ECMs and X13 motors, is that you are able to use static pressure much more accurately as a means to anticipate true airflow, because you don't have to get it as exact. Whereas with a PSC motor, a 0.1 change in static pressure could change your airflow quite a bit. On your average X13 or ECM motor, if you look at the fan tables, it's generally not going to change it any significant amount until you get to 0.8, 0.9 in that range.
Okay, well, I think you're getting two things sort of mixed up. Having a more constant static pressure, in other words, the fact that the fan has very laminar characteristics, it doesn't drop way off, like a PSC motor, when you're looking at the fan tables and you're looking at the RPM and the torque and all that kind of stuff, the PSC motor tends to drop off. The ECM motor, it's going to go the opposite direction because it's going to try and keep the airflow the same. It doesn't make static pressure any more accurate or easy to use. I mean, if we're talking about measuring airflow using static pressure, the fact that it's reading a constant static pressure doesn't mean anything if we can't get a good measurement to begin with. It's still got all the same inherent inaccuracies. It just doesn't have the variability. We're talking about two different things here. We're talking about variability of a measurement versus accuracy of a measurement, unless you're thinking differently.
No, I am, because here's what I'm saying is that, okay, let's say you say, all right, you look at a fan table for an X13 2-ton Carrier FV002 air handler, okay? So you pull open the fan table for that, and you look down and you see where it says, okay, if you put it on tap 3, you're going to produce 800 CFM, all right? So you track that tap 3 and you watch that curve all the way up, and that curve, it's going to produce 800 CFM all the way from 0.3 all the way up to 0.9. And so you can pretty much, if you're calculating system capacity, you can count on that you're going to have 800 CFM.
I got you.
As long as you're in that range.
I got you.
And so even though your measurement's not going to be nearly as accurate, and you haven't fixed the inaccuracy with the measurement,
it becomes less
if you're reading 0.5,
right,
it becomes less important. And so you can go ahead and say, all right, I can be pretty confident that I'm at 800 CFM, or at least thereabouts.
Yeah, I misunderstood what you were saying. Yeah,
do.
No. You're correct right there. Yep. Yeah, that's a correct statement. And that's the nice thing about a constant torque motor is it's going to have those types of characteristics. The only thing that you got to remember is that, again, it's dependent upon the fan and the housing that's in there. So the motor itself, like you can't go out and buy a green speed motor and just retrofit it in there and know exactly how many CFM it's going to move. You're going to have to actually measure the CFM, because you're talking about two different things. One's an engineered system where manufacturers selected the blowers, selected the motors, selected the taps, and they've got everything set up for the right CFM for the system design. And then a retrofit motor, it's not going to give you the same characteristics. You're going to have to measure that CFM.
Right.
Then you'll be good to go.
Yeah, it's going to be extremely tough unless you actually measure the CFM. And this comes up in a lot of cases, but you see one particular case is you'll see guys who try to match model numbers on ECM blower motors or even X13s. And they say, well, I'm going to replace this model with this model. I have it on my truck or it was sitting on the shelf in the shop. And that doesn't work because it's contingent not on the model number of the ECM, but on the program that's in that particular motor. And so you can't just grab something off the shelf that looks the same or has the same product number on it. It's not necessarily going to work.
That is 100% correct. Yeah, and that's, I think, if there's a challenge with using ECMs over PSCs is the fact that all of a sudden we're required to have a very specific motor in the furnace. But if you design the duct system properly, the lifespan of that ECM motor is going to be probably easily 20 years. I mean, they're very good motors. They have a lot less heat that's generated because they're using permanent magnets in the motors. Normally they're ball bearing. A lot of times they're just a better, higher quality motor. Are they expensive? Oh yeah, they're very expensive. But over their lifetime, if they're installed on a well-designed duct system, the motor's going to more than pay for itself in energy savings. And it's going to also give you a much better characteristics over time. Because the other thing is, as the blower wheel gets a little bit dirty, the ECM is just going to speed up and it's going to try and keep the mass flow rate across the coil. So the interesting thing is when the system finally gets to the point of failure, it can be very, very dirty and the blower needs a lot of cleaning and the system's pretty filthy. But overall, you haven't had a huge drop in performance as far as the cooling performance goes. But maybe your electrical consumption is high because your ECM's just running as hard as it can to try and move the airflow. And that's due to a dirty blower or dirty filter or dirty coil or whatever it's seeing because it's just seeing that drop in torque, and it's trying to speed up the fan, to keep the airflow the same.
All right, thank you for listening to the podcast. A couple little loose ends that I like to tie up. One thing that you can always do that helps the podcast, if you aren't subscribed to the podcast, and if you don't know if you are, then you aren't, you can go to any podcast app, and all you have to do is go on your phone, go to the App Store. If you have an Android, go into your App Store and look for the Stitcher app, download that app, search HVAC, find our podcast, and then podcast. I don't even know how to say podcast. Find our podcast and hit the subscribe button. If you have an iPhone, you've already got the podcast app. It's a little purple radio tower looking thing. You can subscribe right there. That's something you can really help us with. If you enjoy the podcast or if you have any feedback for us, we would always ask you to leave us a review if you're willing. It's kind of tricky to do. You have to search the podcast again and then hit reviews and then leave a review. So it's not the easiest thing in the world to do, but it's really helpful for us if you do that. But the biggest thing is just tell your friends. If you have somebody who's, say they're an old timer and they don't know how to use their phone or they don't know how to listen to a podcast, you just show them, download it for them on their phone and show them how to listen. A lot of people don't really, kind of have a hard time. How do you connect it to your car stereo? How do you do this or that? One thing I suggest is, get a set of Bluetooth headphones, or just not headphones, but the ones that just kind of hang around your neck and you have the earbuds. Those are really nice for hands-free anyway. And it's a really great way to listen to some podcasts. Jeremy Smith listens to podcasts when he's in motor rooms, and it helps protect his hearing as well. So you're kind of doing double duty. There's a lot of different ways that you can consume podcasts, but the easiest way to do it is on your phone, either using a Bluetooth headset or connecting it to your car stereo. Finally, I want to let you know about a new product that we're using in my business, and this is called the Pipe Wiper, which is an interesting name, but it's made by Ajax Manufacturing, and you can find it and actually purchase it by going to Jax Manufacturing. So you just do an A, then a dash, then jaxmanufacturing.com. It's called the Pipe Wiper. And that product is essentially, all it is just foam pigs that you shoot through the liquid and suction line instead of using a solvent flush. Because if you've read some of the recent Carrier bulletins on this subject, a lot of manufacturers, and Carrier included, are saying they really don't love the idea of solvents. Because solvents, like RX-11 flushes and those sorts of things, they can leave a residue in the lines that can then be more harmful to the system than any residual mineral oil might be. The nice thing about the Pipe Wiper is it's not chemical, it's not going to get in your employees' eyes, it's not going to damage anything, and if it ever gets stuck, because a lot of guys say, it's going to get stuck. Well, they've proven that unless the kink is greater than 50% of the diameter, it won't get stuck. So first of all, if it does get stuck, that kind of tells you something's wrong. But all you have to do is just blow it back the other way with nitrogen. It's not a cheap kit, but it's a kit that will easily pay for itself if you've been using flush products. So it reduces the amount of nitrogen you have to use, it reduces the amount of flush you have to use, and you can get a 5% discount on that when you buy it from their website by using our offer code, which is GetSchooled. No spaces, no caps, just get schooled, which is, coincidentally is the same offer code that you can get an 8% discount at TrueTechTools.com for anything that you buy. And I encourage you to look at all of the Testo I-Series products. So 605Is, 510Is, all those products, the Bluetooth connected products. You can do a lot of things with those tools, and it can make your life a lot easier. Anyway, we're going to have the next episode of this, the airflow episode, coming up in a couple days, so keep watching out for that. And in the meantime, just keep doing good work out there. Thank you for listening. We'll talk to you next time on the HVAC School Podcast. Oh, wait, real quick. I'm sure you've been waiting this whole time because I mentioned an inside joke at the beginning, which is the chicken joke that I told Jim. And of course, it's a little hard to do without anybody on the other side, but I'm going to do my best. So I'll play both parts here. I'll play me and Jim. So I asked Jim. I say,
"So Jim, why did the chicken cross the road?"
And so then Jim says,
"I don't know, Brian. Why did the chicken cross the road?"
And I say,
"To visit the ugly guy."
And then Jim's like,
"What?"
And then I'm like,
"Knock, knock."
And Jim's like,
"Who's there?"
And I'm like,
"The chicken."